New theory challenges Big Bang, universe's origins reimagined. Imagine a universe that doesn't require mysterious, unproven elements to explain its birth. A cosmos shaped purely by the forces we already know, gravity and quantum mechanics. Sounds too good to be true? Well, a team of scientists led by Raúl Jiménez, an ICREA researcher at the University of Barcelona's Institute of Cosmos Sciences, ICCU, in collaboration with the University of Padua, Italy, has just unveiled a revolutionary theory that could rewrite the story of how everything began. This groundbreaking study was published in the esteemed journal Physical Review Research, and this is where it gets fascinating. What if the answers have been hiding in plain sight all along? For years, cosmologists have relied on what's known as the inflationary paradigm to describe the universe's explosive growth in the moments after the Big Bang. The idea is straightforward enough at first glance. Within a fraction of a second, the universe expanded at an unimaginable rate, stretching out from a tiny speck into the vast expanse we observe today. But dig a little deeper, and you'll find that this model comes with a major drawback. It depends heavily on adjustable variables, or free parameters. These are essentially dials that scientists tweak to make the model fit observations. The problem? Too many free parameters make it hard to distinguish between genuine predictions and mere data-fitting exercises. But here's where the new theory takes a bold step forward. Instead of leaning on speculative fields or exotic particles, the researchers propose a model rooted in de Sitter space, a well-understood cosmic state consistent with modern discoveries about dark energy. In this framework, the early universe didn't need any arbitrary adjustments or mysterious ingredients to set the stage for everything we see today. It started with conditions that align perfectly with what we already know about the cosmos. Doesn't that sound refreshingly simple? Now, let's talk about gravitational waves. Those ripples in the fabric of space-time that Albert Einstein predicted over a century ago. These waves aren't just fascinating phenomena. They might hold the key to understanding how galaxies, stars, and planets came to exist. According to the new model, spontaneous quantum fluctuations in space-time during the universe's infancy created tiny density variations. Over billions of years, these subtle differences grew and interacted non-linearly, eventually forming the complex structures we observe today. Unlike earlier theories that relied on hypothetical particles or fields, this approach uses only real, observable physics to explain cosmic evolution. Raúl Jiménez sums it up beautifully. For decades, we've tried to understand the universe's beginnings using models based on what makes this proposal so exciting is its simplicity and testability. We're not inventing new components. We're showing that gravity and quantum mechanics alone might suffice to explain the formation of the cosmos. If this theory stands up to scrutiny, and that's a big if, it could mark a turning point in our quest to understand the universe's origins. Imagine being able to describe the birth of galaxies without needing to invoke unknown particles or speculative assumptions. The implications would ripple far beyond astrophysics, reshaping how we think about science itself. Of course, not everyone will agree with this radical shift. Some may argue that abandoning the inflationary paradigm altogether is premature, especially given how much it has contributed to our understanding so far. Others might question whether gravitational waves alone can account for the rich tapestry of cosmic structure. And this is the part most people miss. Every scientific breakthrough invites debate and skepticism, and rightly questioning the status quo what drives progress. So, what do you think? Could this new model truly replace decades of established thinking? Or does it raise more questions than it answers? Share your thoughts in the comments below. We'd love to hear whether you find this theory compelling or controversial. Harvard and Cambridge scientists challenged the Big Bang inflation theory. Imagine a discovery that could rewrite the history of the universe itself. Two leading astrophysicists from Harvard and Cambridge are challenging the widely accepted theory of cosmic inflation, a cornerstone of the Big Bang model. Dr. Sunny Vagnozzi, now at the University of Trento, and Professor Avi Loeb of Harvard University, propose that a specific signal, the cosmic graviton background, CGB, could potentially disprove cosmic inflation if detected. This bold claim opens a new chapter in our understanding of the universe's earliest moments. Cosmic inflation, a theory introduced to address inconsistencies in the Big Bang model, suggests that the universe underwent a rapid expansion immediately after the Big Bang. This expansion helps explain why the universe appears so uniform and why galaxies are distributed as they are. However, the theory has faced criticism for being overly flexible, allowing it to adapt to almost any observational data. This flexibility has led some to question whether inflation is truly a scientific theory or merely a convenient framework. Vagnozzi and Larobe argue that the CGB, a relic radiation from the earliest moments of the universe, could provide a definitive test. Unlike the cosmic microwave background, CMB, which is the oldest light we can observe, the CGB is a signal from gravity itself. If it exists, it would have originated just 10 to the power of negative 43 seconds after the Big Bang, during the Planck time, when the universe was incredibly hot, around 10 to the power of 32 degrees. According to the researchers, the CGB should still be present today as a faint thermal glow at about 0.9 Kelvin. If detected, this would directly contradict the predictions of inflation, which states that the massive expansion during this period would have diluted any early graviton background to the point of being undetectable. But here's where it gets controversial. If the CGB is found, it could not only disprove inflation but also offer insights into quantum gravity, a field that seeks to unify general relativity and quantum mechanics. Detecting the CGB is no small feat. The signal would consist of high-frequency gravitational waves, peaking around 100 GHz, far beyond the capabilities of current detectors like LIGO and Virgo. However, Vagnozzi and Loeb remain optimistic. They suggest that next-generation cosmological probes could detect indirect signs of the CGB by measuring subtle changes in the universe's expansion rate. Specifically, the presence of the CGB would slightly increase the number of relativistic species, or fast-moving particles, in the early universe. While a direct detection of high-frequency gravitational waves would be the ultimate proof, indirect evidence could still point us in the right direction. And this is the part most people miss. The search for the CGB offers a clear, binary test for inflation. If the CGB is found, inflation as we know it is likely incorrect. This would be a monumental discovery, potentially reshaping our understanding of the universe's origins. The implications of finding the CGB extend beyond just disproving inflation. It could also provide a window into the earliest moments of the universe, less than a trillionth of a second after the Big Bang. Additionally, it could offer new tools to test quantum gravity theories, which have long been a holy grail for physicists. What if the universe didn't start with a bang, but with a bounce? This is a question that Loeb and others have pondered, and the CGB could provide crucial evidence. The challenge is immense, but the potential rewards are cosmic. Detecting the CGB would not only challenge a fundamental theory, but could also lead to groundbreaking discoveries in physics. What do you think? Is the search for the CGB worth the effort, or do you believe in the robustness of inflation theory? Share your thoughts in the comments below. Not Big Bang, a new theory of the universe's birth. Imagine a world where the origins of the universe are explained not by the explosive Big Bang, but through the elegant interplay of gravity and quantum physics. This is the intriguing premise of a recent study conducted by researchers from the Universities of Barcelona and Padua, which boldly challenges the long-standing inflation theory that has dominated cosmological thought for decades. While inflation has been a cornerstone in explaining the universe's structure, it often leans on speculative concepts involving unknown particles and unobserved forces. But here's where it gets controversial. This new theory proposes a more straightforward explanation that relies solely on established principles of physics. The researchers argue that the universe began in a stable state known as de Sitter space, a concept that aligns with our current understanding of dark energy. In this framework, the early universe was characterized by a uniform and smooth expanse, devoid of matter and light, yet rich in the energy of space itself. Within this environment, tiny quantum fluctuations, essentially minute ripples in the fabric of space and time, naturally emerged. Over time, these fluctuations evolved into gravitational waves, which played a crucial role in creating the density variations necessary for matter to coalesce, ultimately leading to the formation of galaxies, stars, and planets. What makes this theory particularly compelling is its simplicity. Unlike the inflation model, which introduces hypothetical fields, like the so-called inflaton, this new approach offers a cleaner and more testable framework. It invites us to reconsider how cosmic structures could arise from fundamental laws of physics, rather than relying on unproven elements. So what exactly is de Sitter space? It is a theoretical construct that describes an expanding universe characterized by a positive cosmological constant, akin to dark energy. This model helps scientists understand the universe's behavior, especially during its early stages or in the far future, when dark energy is expected to dominate. Now you might wonder, does this theory completely dismiss the Big Bang? Not at all. Instead, it presents a fascinating alternative perspective. It suggests that the universe may not have originated from a cataclysmic explosion, but rather from a stable, expanding state governed by gravity and quantum mechanics. This minimalist approach reshapes our understanding of cosmic origins, emphasizing how structure can emerge from the fundamental laws of nature. The implications of this theory for the scientific community are significant. It stands out because it makes predictions that can be tested through observable phenomena, particularly in the realms of gravitational waves and cosmic structure. Lead author Raúl Jiménez describes the proposal as simple, elegant, and powerful, highlighting its avoidance of introducing unobserved elements merely to satisfy mathematical requirements. If this theory is validated through future research, it could mark a monumental shift in our comprehension of the universe's beginnings. As we delve deeper into these ideas, it raises thought-provoking questions. Could our understanding of the cosmos be on the brink of a revolutionary change? What do you think about this new perspective on the universe's origins? Join the conversation in the comments below.